Now, what we will do is we will look at other quantities. See, what we have seen is only the DC side voltage so far. So, we are considering what is known as 2 and 3 valve conduction mode. So, we will continue with the discussion on 2 and 3 valve conduction mode and look at other quantities for 2 and 3 valve conduction mode. Here we have 2 subintervals in each interval. So, that means in one cycle we have 12 subintervals. So, if there are 6 intervals and 2 subintervals in each interval, in cycle we have 12 subintervals. So, we will form a table as in the case of zero overlap angle. So, see, the purpose of forming a table is to show that what is the expression for the DC side voltage, instantaneous DC side voltage in each subinterval, and what is the voltage across a valve. Okay. So, we will list all the subintervals. So, I will take the first column of the table where I show the subinterval. In the second column, I show what are the valves that conduct. Then the expression for the instantaneous DC side voltage Vd. And I show finally the voltage across valve 1. So, what is the first subinterval? So, we always take the starting point as the instant of turning on valve 3. So, valve 3 is turned on at alpha. So, the first subinterval is from alpha to alpha plus u. So, let me first write down all the subintervals. The second subinterval is alpha plus u to alpha plus 60 degrees. So, then it is straightforward, alpha plus 60 degrees to alpha plus u plus 60 degrees, then alpha plus u plus 60 degrees to alpha plus 120 degrees, alpha plus 120 degrees to alpha plus u plus 120 degrees. Alpha plus u plus 120 degrees to alpha plus 180 degrees, alpha plus 180 degrees to alpha plus u plus 180 degrees, alpha plus u plus 180 degrees to alpha plus 240 degrees. Alpha plus 240 degrees to alpha plus u plus 240, alpha plus u plus 240 degrees to alpha plus 300 degrees, alpha plus 300 degrees to alpha plus u plus 300 degrees. Then alpha plus u plus 300 degrees to alpha plus 360 degrees. So, that completes one full cycle consisting of 12 subintervals. So, let us look at the second column, valves that conduct. In the first subinterval, what are the valves that conduct? 1, 2 are already conducting. So, 3 is turned on. So, as soon as 3 is turned on, 1 will not stop conducting, it will continue to conduct. So, it is 1, 2, 3. So, at alpha plus u, valve 1 stops conducting. So, the valves that are conducting in the subinterval 2 is are 2 and 3. Then at alpha plus 60, valve 4 is turned on, 2 and 3 are already conducting. At alpha plus u plus 60, 2 stops conducting. So, it is 3, 4. So, similarly, we can just write down what are the valves that conduct: 3, 4, 5, 4, 5, 4, 5, 6, 5, 6, 5, 6, 1, 6, 1, 6, 1, 2, 1, 2. Then again the cycle repeats. Then the next column is VD. We got the expression for VD in the first subinterval. What was the expression? We derived it in the last class. So, you can write it in terms of EA, EB, EC. So, it is 3 by 2 minus 3 by 2 EC, okay, minus 3 EC by 2. The expression for VD in the second subinterval is EB minus EC. Now, it is easy to get the expression in the second subinterval because there is no drop across the inductance. Okay. So, from the circuit we can straight away say what is the expression for the DC side voltage in the second subinterval. That is, in all the subintervals where only 2 valves are conducting, it is straightforward. Okay. So, let us try to fill this column. First of all, we will try to fill the column, the rows which are easy to do. Okay. So, for the sake of let me just take the circuit of the converter. So, using the circuit I will be able to fill the entries in the table. So, this is our circuit. So, let us go back to the table. So, as I said, it is easy to fill the third row, the third column wherever there are only 2 valves that conduct. So, if I take the fourth subinterval, 2 valves are conducting, 3 and 4. So, when 3 and 4 are conducting, so 3 and 4 are conducting. So, when 3 and 4 are conducting, the current ID is passing through the inductance which is connected in series with EB, and it is also passing through the inductance which is connected in series with EA. Say when 3 and 4 conduct, the voltage sources, the single phase voltage sources through which there is a non-zero current is EA and EB. So, the inductances which carry the same current ID will not have a voltage drop across it because current is constant. So, due to which I can easily write the expression for VD. So, when 3 and 4 conduct, the anode and cathode of 3 are at the same potential and they are same as the potential of the positive terminal of what? EB. So, that is nothing but the positive terminal of VD. The negative terminal of the DC side is actually connected to the positive terminal of EA, because L acts as a short circuit. Of course, our thyristor valve is a short circuit. So, we can easily say that the expression for VD is EB minus EA. So, I will come to the third row shortly. I will just fill the easier ones first. Then, if I come to the fifth subinterval, again there are two valves conducting 4 and 5. So, when 4 and 5 conduct, so can I say what is the expression for VD? 4 and 5 conducts, EC minus EA. So, EC minus EA. Then 5 and 6 conducts, EC minus EB. Six and 1 conducts, EA minus EB. Then 1 and 2 conduct, EA minus EC. Okay. Now, let us fill the other rows. There is a third subinterval with in which 3 valves are conducting, 2, 3, 4. Now, should I do a derivation similar to the one that was done for first subinterval? So, can I get an expression for the instantaneous DC side voltage VD in the third subinterval when 2, 3 and 4 conduct without doing any derivation? I mean, how do we get? I mean, let us get see the expression later, but can I try to get an expression without going through the derivation? Say we got the derivation for the first subinterval minus 3 by 2 EC. How did you get that? Yeah, say if you look at the DC side voltage, the DC side voltage repeats after what? Every 60 degrees. So, the point is, if I take VD at instant omega OT plus 60 degrees, it is equal to VD of omega OT. Now, if I want to satisfy this equation, that means VD being periodic with period 60. Of course, it's periodic with period multiples of 60 also. We are using that fact to say that all our waveforms have a period which is 360 degrees, but it is also having a period of 60 degrees. Okay. So, using that, can I say that I can get an expression for VD in the subinterval in terms of EA, EB, EC? So, I have to take, instead of minus EC, some other waveform which is lagging or leading EC by 60 degrees. So, which voltage is lagging or leading EC by 60 degrees? Should I take lagging or leading? See, the first subinterval has minus 3 by 2 EC. Okay. So, what is the expression for EC? Okay, let us look at the expression for EC. EA is root 2 by 3 V sin omega OT plus 150 degrees. EB is root 2 by 3 V sin omega OT plus 30 degrees. EC is root 2 by 3 V sin omega OT minus 90 degrees. Okay. So, these are the expressions of the 3 voltages. Now, the negative of these 3 voltages and these 3 voltages themselves form 6 voltages which are equal in magnitude and displaced by 60 degrees. So, if I take minus EA is root 2 by 3 V sin omega OT What is the phase angle of minus EA? Of course, if I restrict myself to minus 180 and 180, so I will restrict the phase angles to be within minus 180 and plus 180. So, it is minus 30, and minus EB is root 2 by 3 V sin omega OT minus 150 degrees. Minus EC is root 2 by 3 V sin omega OT plus 90 degrees. So, you see that this EA, EB, EC, minus EA, minus EB, minus EC are all having the same RMS value, and they are 60 degrees apart. Okay. So, what I can do is use this information and also the fact that the DC side voltage is periodic with 60 degrees, I can get an expression for VD. So, what I have to do is I have to take some voltage among EA, EB, EC, minus EA, minus EB, minus EC, which is actually lagging minus EC by 60 degrees. So, look at minus EC. Minus EC is having a phase angle of plus 90 degrees. So, which waveform is lagging minus EC by 60 degrees? EB. So, EB. So, that means this expression will be 3 EB by 2. Is that okay? Then in the fifth subinterval, I have to take a waveform which lags EB by 60 degrees. Again, if you look at EB is actually 30 degrees. So, something which lags EB by 60 degrees is minus EA. Is it? I mean, what is the waveform? Minus EA. So, it is minus 3 EA by 2. Okay. Then for the subinterval in which valves 4, 5 and 6 conduct. So, minus EA is having a phase angle of minus 30. I have to get a waveform which lags this by 60 degrees. So, it should have a phase angle of minus 90, which is nothing but EC. So, this is 3 EC by 2. Then the subinterval in which 5, 6, 1 conducts is 3 by 2 into some waveform which lags EC by 60 degrees. So, EC is having a phase angle of minus 90. So, which waveform lags EC by 60 degrees? So, EC is having a phase angle, okay, EC is having a phase angle of minus 90. Yeah, minus EB. Minus 3 EB by 2. Then we have to next take the waveform which lags minus EB by 60 degrees, which is EA. 3 EA by 2. Now, let us look at voltage across valve 1. Some of the entries are very easy. Whenever a valve is conducting, voltage across the valve is 0. So, the first subinterval voltage across valve 1 is 0. Let us write the easier ones first. The last 4 subintervals, if you see, the last 4, in all these 4 subintervals, 1 is conducting. So, it is 0 there also. Now, let us come to the second subinterval, alpha plus u to alpha plus 60 degrees, valves 2 and 3 are conducting. What is the expression for V? So, voltage across valve 1 is EA minus EB. So, there is no current through the inductance connected in series with EA. So, the positive terminal of EA is at the same potential as anode of valve 1, and the cathode of valve 1 is at the same potential as the positive terminal of, see, 2 and 3 are conducting. So, the cathode of valve 1 is same as the positive terminal of EB. So, the voltage across valve 1 is EA minus EB. So, let us again do the easier ones first. Let us take the subinterval in which two valves 3 and 4 are conducting. So, when the valves 3 and 4 are conducting, what is the voltage across valve 1? EA minus EB. Then valves 4 and 5 are conducting, EA minus EC. Then when valves 5 and 6 are conducting, EA minus EC. Now, let us come to the subintervals in which 3 valves are conducting. If I take the third subinterval, valves 2, 3 and 4 are conducting. Let us come to this circuit. So, valves 2, 3 and 4 are conducting. What is the voltage across valve 1? EA minus. Now, you have to note that when 3 valves are conducting, the drop across inductance is not 0. Only when 2 valves are conducting, the voltage across the inductance is 0 because it is constant. Huh? I did not get. Can you please? Oh, okay. So, okay. So, what you are saying is here the voltage is 0. Yeah. So, will that answer the question?
EA minus LDI by dt minus V required minus VD is equal to.
No, the point is what he is saying is when valves 2, 3 and 4 are conducting, the voltage across this inductance in series with EB is 0. From that, can I get an expression for the voltage across valve 1? EA minus? Yeah, but the point is this is not 0. The voltage across the inductance in series with EA is not 0. This may be 0. See, the valve 4 is also conducting. So, where should the current through valve 4 flow? It should flow through one of the sources on the AC side. So, it will flow through EA. So, this current is actually not constant. So, this is not equal to 0.
EA minus EA minus EP minus EC by 2 omega and 2 LS.
Yeah. See, what I want is an expression in terms of EA, EB and EC. See, I am trying to get expressions in terms of EA, EB and EC. Can I write it in terms of VD? What is the voltage across valve 1 in terms of VD in this case? Valves 2, 3 and 4 are conducting. Can I write it in terms of VD? No, why in terms of VD means we already know what is VD. So, if I know in terms of VD, it becomes easy. See, VD I have already written in terms of EA, EB and EC. So, the hint is there is an easy relationship to VD. See, in a leg, see, let me just explain. Suppose I have these 3 points A, B, C. Okay, these are the AC side terminals A, B, C. This is called leg A, leg B, leg C. Now, if I take leg A, when 4 is conducting, voltage across valve 1 is, what is voltage across valve 1? No, see, when I say voltage across valve 1, I have defined the voltage across a valve. It is voltage of anode with respect to cathode. So, it is minus VD. So, voltage across valve 1 when 4 is conducting is minus VD. Is that fine? So, I need not do any derivation. I can just say it is minus VD, which happens to be minus 3 EB by 2. So, if I want in terms of EA, EB, EC, it is minus 3 EB by 2. Is that okay? So, I need not do any further derivation. So, the result I am using is I am trying to express the voltage across valve 1 in terms of VD, that is all. So, when 4 is conducting, the voltage across valve 1 is minus VD. Okay. Now, let us go back to the table. So, if I go to the subinterval in which valves 3, 4 and 5 are conducting. So, even here 3, 4, as long as 4 is conducting, voltage across valve 1 is minus V d. Okay. So, it is minus V d. So, minus V d, but it is not the same expression in terms of E A B C. Look at the expression for V d now, it is minus 3 E A by 2. So, this will be 3 E A by 2. Then what about now the next subinterval in which 3 valves are conducting, 4, 5, 6, again 4 is conducting. So, when 4 is conducting, it is again minus V d. So, it is minus 3 E C by 2. Is that clear? Now, using this table, we will look at the voltage jumps across a valve. Voltage jumps. So, how many voltage jumps are there? See, voltage jump means the discontinuities in the voltage across a valve. So, these discontinuities are ideal because we have neglected the switching times, the time taken to go from on state to off state or off state to on state. Okay. So, since we are neglecting that, there is a discontinuity, but in practice it is a large rate of change of voltage which has to be taken care of. So, the valve has to be designed to withstand these rate of change of voltages. So, how many jumps are there? 8. Yeah. There is a jump at the end of first subinterval, there is a jump at the end of second, third, fourth, fifth. No, there is a jump at the end of first subinterval itself, then 7th, 8th. Okay. So, let us try to get an expression. So, what I will do is I will not try to derive this expression for voltage jump. So, what you have to do is take the expression for E A minus E B and substitute for omega O T what value? First jump. The first jump is at the end of the first subinterval. So, alpha plus u. So, you have to just substitute alpha plus u for omega O T in the expression for E A minus E B. So, I will leave it to you to show that this is minus root 2 V sin alpha plus u. So, minus root 2 V sin alpha plus u. So, it is say the jump is actually at alpha plus u, and the jump actually is E A minus E B minus 0, that is all. It is E A minus E B minus 0. Similarly, the next jump is minus 3 E B by 2 minus E A minus E B evaluated at alpha plus 60 degrees. So, this jump you can verify. So, I will just give the result, I will leave it to you to verify. V by root 2 sin alpha, the second jump. Then the third jump at alpha plus u plus 60 degrees is minus V by root 2 sin alpha plus u. Now, please note the jumps, we cannot say whether the jumps are positive or negative looking at this expression, it depends on alpha and u. Okay. So, only restriction on u is it is less than, the only restriction we have put on u is it is less than 60 degrees, that is all. Okay. So, we have not put any restriction on alpha, and of course, V is RMS value. So, it has to be positive. Then the third jump is minus V by root 2 sin alpha plus u. The fourth jump is minus V by root 2 sin alpha. Then it is minus V by root 2 sin alpha plus u, minus V by root 2 sin alpha, V by root 2 sin alpha plus u. The last jump is 0 minus E A minus E C evaluated at alpha plus 240, it is minus root 2 V sin alpha. So, we have got the expressions for the voltage jump. So, the idea is the rate of change is actually not infinity. The rate of change is nothing but the entries in the last column, the voltage jumps, divided by the switching time, the time taken to go from on state to off state or off state to on state. I mean, that is dependent on the device. Okay. So, based on that value of the time that goes in the denominator, this comes in the numerator. Okay. So, do not go by the ideal characteristic of the device that we are using, that will give infinite. So, in practice it is not infinite, the rate of change of voltage is not infinite.